For weeks, the trajectory of 3i Atlas has been shifting with quiet precision. On the surface, it appears passive, an interstellar visitor passing near Mars before vanishing behind the Sun. But the data gaps are growing louder. High-resolution imaging from multiple agencies expected during its Mars flyby never arrived. Instead, a blackout. No confirmed frames. No released measurements. And just ahead, a maneuver window is opening. This silence isn't random. It's timed against the object's lowest inclination passed through the inner solar system in decades, an arrival angle so statistically rare it forces the question of intent versus coincidence. That window closes when 3i Atlas disappears behind the Sun on October 29th. Amid the silence, unverified leaks claim its thermal and chemical behaviour doesn't match cometry models. A debated navcam streak has fractured the scientific conversation further. And at the edges of this unfolding story, a single vector draws unease, a directional proximity between the object's trajectory and the 1977 WOW signal. These threads aren't proof, but they are pressure points. At the same time, telescopes, laboratories, and AI systems across the globe are accelerating, reshaping the scientific landscape in which this anomaly is being decoded. This is not just about a single object anymore. It's about the tools, the data, and the stories being told in their absence. The Mars flyby should have been one of the cleanest observation opportunities since 3i Atlas entered the inner solar system. Its trajectory was projected to pass within a range that multiple orbital assets could observe, including high-resolution cameras mounted on Mars orbiters and surface-based navcams designed to track fast-moving objects against the Martian sky. Yet, as the object passed the closest point of its approach, the stream of expected images never arrived. The silence was immediate and deliberate. On mission dashboards that typically update within hours, the relevant observation directories stayed blank. Data transfer windows closed without the usual trickle of raw frames. Public access archives remained unchanged. The flyby came and went, leaving a conspicuous absence where visual confirmation should have been. This absence set off a cascade of technical speculation. Engineers and astronomers know how these windows work. Observing an object during a near-planetary pass is standard procedure. Orbital images like those circling Mars can achieve resolution sharp enough to detect activity on the object's surface. Even a single clean frame would have clarified its reflectivity, albedo, surface structure, and potential outgassing patterns. But instead of sharp clarity, the world received silence, and that silence was timed with precision. Some explanations are benign: solar angle interference, instrument prioritization for other missions, temporary downlinks. But not everyone accepts that. Internal schedules reportedly indicated a dedicated imaging block for the event. Multiple observation teams had filed confirmed tracking requests weeks in advance. It wasn't a missed shot, it was something that changed at the last moment. This is where the fracture began. On one side, officials suggested the imaging window simply didn't align with the optimal angle and available bandwidth. On the other, independent analysts pointed to a pattern. Data suppression during high-value windows has now happened more than once. First during the inbound Venus alignment, now at Mars. Two separate opportunities, two identical silences. The timeline is precise. The flyby occurred over a 6-hour window with optimal imaging in the final 90 minutes. Ground stations expected at least partial confirmation frames within 12 hours. None were logged. Days later, only a brief, low-resolution spectral trace appeared, and even that trace has been contested. Critics argue it lacks proper metadata, with timestamp irregularities suggesting post-event interpolation rather than direct observation. Meanwhile, among deep space analysts, the conversation shifted from what was seen to why nothing was shown. Did the object behave unexpectedly? Did the imaging reveal features that agencies are unwilling to disclose? Or did a more subtle issue occur, a classification cascade triggered by something in the raw data itself? The silence had consequences. Amateur astronomers and private observatories, often dismissed as fringe voices, gained new momentum. With state channels quiet, speculation filled the vacuum. Claims of light fluctuations, unexplained signal spikes, and local tracking inconsistencies began circulating across monitoring networks. None of these claims rise to hard evidence, but they have traction precisely because the expected data is missing. This is how credibility fractures. In the absence of frames, theory becomes currency. and the most persistent theory is that something about 3 I-Atlas's behaviour near Mars was unexpected enough to vanish behind a wall of delay. Whether or not that's true remains unproven, but one fact stands unshaken. The highest resolution eyes we had on the object went dark at the critical moment, and this brings the investigation to the next anomaly, not what happened at Mars, but how the object is moving. Its path through the solar system isn't chaotic, it's eerily aligned. A low inclination trajectory so clean, so rare, it sits well outside expected probabilities. If you trace the path of 3I Atlas across the inner solar system, what emerges is not a chaotic swing through gravitational currents. It's a calculated glide. From the moment it was first observed, its trajectory has remained locked with unnerving precision to the plane of the ecliptic. That flat, almost invisible sheet on which all major planets orbit is not a random reference frame. It's the solar system's backbone. The vast majority of interstellar objects arrive at steep angles to this plane. They cut through it, like a spear slicing water. 3I Atlas, however, doesn't cut. It rides it. Orbital data from the European Space Agency and NASA confirm an inclination of just 1.17 degrees. For comparison, the previous known interstellar visitor Oumuamua entered at nearly 33 degrees. Even Comet 2 I/Borisov, a far more typical interstellar object, had an inclination exceeding 40. Statistically, trajectories this flat are outliers, and the numbers are brutal. Less than 0.2% of modelled interstellar orbits fall this close to the ecliptic plane. Why this matters isn't just a question of math, it's a question of behaviour. A shallow inclination maximises an object's interaction time with multiple planets. Instead of slicing through the system in weeks, 3I Atlas has been coasting along an orbital lane that allows gravitational assists, synchronised flybys, and extended periods of low-energy drift. It is, effectively, moving as if it knows how to stay in the quiet zones of the solar system, not in the loud, high-inclination trajectories that attract immediate attention. To understand how rare this is, imagine the solar system as a paper-thin disk with planets moving along its surface. Interstellar visitors usually approach like darts thrown at that disk from above or below, punching through and vanishing into deep space. But 3I Atlas is like a marble rolling along its surface, matching its geometry so closely that its gravitational interactions aren't collisions, they're alignments. This is why orbital analysts started whispering a single word: intentionality. This doesn't prove control, but it does narrow the probability space drastically. Natural processes can sometimes create trajectories that mimic low inclination entries. For example, ejected debris from stellar nurseries can occasionally inherit rotational and orbital alignments that make them appear unusually flat. But in those cases, the velocity profiles tend to be messy: microperturbations, subtle variations caused by uneven gas jets, long-term drag from solar wind pressure. 3I Atlas shows none of these. Its trajectory has remained razor straight. Consider the Earth's orbital neighbourhood. Any object crossing this region at such a low inclination will intersect multiple gravitational wells almost perfectly: Mars, Earth, Venus and Jupiter further out. Each flyby creates opportunities for slingshot manoeuvres or gravitational braking without requiring significant propulsion. If an object wanted to stay in the system longer than a typical flyby time, this is the path it would choose. It is in many ways the cleanest lane through the system. It's the difference between dropping a stone through water and skimming it across the surface. And then there's the timing. 3I Atlas is scheduled to slip behind the Sun on October 29th, a moment that isn't just astronomically interesting but operationally critical. When an object moves into solar conjunction, ground-based observation networks lose optical contact. Radio and radar tracking can continue, but only at reduced fidelity and with heavy interference. It is quite literally the best possible time for something to disappear. This window isn't accidental. Its Mars flyby occurred just 18 days before solar conjunction, a geometry that places the object at peak visibility, then immediately in the shadow of the Sun. If this were a mission trajectory planned by human engineers, it would be elegant. You approach when everyone can see you just enough to confirm you exist. Then you vanish into a region where no one can fully track your maneuvers. Skeptics point out that coincidence is still possible. The galaxy is vast. Statistically improbable events do occur, but probability alone doesn't account for stacking anomalies. a missing imaging window at Mars, a razor-thin inclination path, a perfectly timed solar disappearance. These aren't independent events. They are a pattern unfolding in sequence, and in orbital dynamics, patterns speak louder than narratives. Even more striking is the velocity profile. Observations have shown almost no sign of chaotic perturbation, no measurable jetting behavior that would normally accompany an object shedding volatile material under solar heating. Instead, 3I Atlas has maintained a clean, stable hyperbolic trajectory, as though its mass distribution were engineered for flight stability. Some analysts describe its motion as dead straight, others prefer controlled drift. If that's the case, then its low inclination arrival isn't just luck, it's a strategic insertion into the solar plane. That corridor allows it to interact gravitationally without revealing much. No unpredictable spin, no tumbling signatures, no visible activity to track, just quiet, steady movement. This leads to an uncomfortable but unavoidable implication. If this object is not behaving like a comet and not behaving like an asteroid, what is it behaving like? The scientific community has fractured along this line. Some argue for exotic natural explanations, a fragment from a galactic disk with coincidental alignment. Others quietly acknowledge that its trajectory bears uncanny resemblance to a low-energy reconnaissance path, a glide along planetary lanes timed to minimize observation windows, and this is where the physical evidence deepens. Because shortly after its low-inclination trajectory became public, an unverified leak surfaced, suggesting thermal readings from the object defied cometry expectations. No one has claimed official authorship of the leak, but the details, if true, are not trivial. The first whispers didn't come from official press releases. They came from the quiet channels, the private mailing lists between observatories, encrypted group messages between engineers, unlisted telemetry dashboards watched by people who don't sleep when something anomalous moves through the solar system. A small packet of data, labelled as originating from an unnamed European tracking station, began circulating on October 3rd. It was a set of narrow-band thermal readings, supposedly taken during the final approach to Mars. At first glance, it looked ordinary, a few lines of raw flux measurements, incomplete timestamps, and an unusual footer notation. But buried in the numbers was something that caught the attention of the analysts who saw it. The temperature curve was flat. Objects like comets don't behave that way. As they approach a planetary body or move closer to the Sun, their thermal signature usually spikes sharply. Sublimation of volatile ices generates heat and uneven plumes of outgassing. Even inert asteroids show subtle gradients as their surfaces absorb and re-radiate solar energy. 3I Atlas didn't. According to the leaked values, it maintained a nearly constant thermal output over a span of 19 hours, a stability that no natural comet on a near-solar trajectory should display. This is where the first red flag was raised. If the data was real, it suggested a surface with either unusual thermal conductivity or an active regulatory mechanism, something capable of distributing heat so evenly that even solar proximity didn't change its emission profile. That isn't behavior seen in icy bodies or rocky fragments, it's behavior more consistent with engineered thermal control. Within days, the leak was quietly analysed by 3 independent astrophysics groups. All reached the same conclusion. If the numbers were real, 3I Atlas was reflecting or redistributing energy in a way that doesn't fit any standard comet model. No known naturally occurring surface composition can maintain that degree of thermal stability at its current heliocentric distance without showing clear radiative peaks or emission tails. And then came the second layer of the leak, the spectral anomaly. Alongside the flat thermal curve, there was a single flagged line in the near-infrared band. It wasn't bright, but it was precise. A narrow emission peak at a wavelength typically associated with complex carbon chains under controlled excitation. Natural comets can produce weak organic signatures, but those signatures are usually broad, diffuse, and unstable. This line was thin and coherent. It didn't look like the messy fingerprint of sublimating ice. It looked like something structured. That's where the scientific debate detonated. Some saw the signature as an artifact, a calibration error, perhaps an instrument glitch during the Mars pass. Others weren't so sure. The stability of the thermal readings, the narrow band of the emission line, and the context, a missing imaging window, and a perfect low-inclination trajectory, made the possibility of error feel less convincing. For those who've worked with thermal data, the anomaly is striking for another reason. It appears deliberately steady, Space is chaotic. Natural bodies fluctuate constantly. They heat unevenly, emit unpredictably, and tumble through solar wind like stones skipping across a current. 3i Atlas seems to do the opposite. It doesn't react, it maintains. And then, in the middle of this quiet storm, an internal memo from a research team circulated privately through academic networks. It stated, in carefully hedged language, that the energy profile currently associated with the object does not match any expected model for a cometary nucleus, stony or metallic asteroid, or carbonaceous fragment at this range. It went further. The thermal uniformity is either the result of a profoundly unique natural phenomenon or the presence of an external regulatory structure. This line changed the tone of the conversation overnight, because thermal regulation, if intentional, would imply something more than passive material. It would suggest either internal energy management or an exotic surface composition engineered to avoid detection. Either option places 3i Atlas far outside the standard catalogue of interstellar debris. Skeptics moved quickly to push back. Some claimed the data couldn't be trusted because its chain of custody was unclear. The leak, after all, was never officially acknowledged. There's no verified station ID attached. Others pointed out that telemetry from planetary flybys is notoriously prone to noise artifacts, and that the clean line in the infrared could easily be a reflection of Mars' own emission spectrum bleeding into the signal. But those counter-arguments couldn't erase the growing unease, because behind closed doors, more people confirmed something similar. Observatories in Chile, Spain and Japan reported flat thermal behaviour in their own limited readings. Nothing as detailed as the leak, but enough to suggest that the initial anomaly wasn't isolated. The object's skin, whatever it is, absorbs energy without the wild temperature fluctuations expected from rock or ice. And here's where the timing sharpens. All of these readings came from the same narrow window between the Mars flyby and its gradual drift towards solar conjunction. That period is the last stretch of sustained observation before the object slips behind the Sun. In other words, if these signals are real, they were captured in the final days when 3i Atlas could still be observed clearly. This is why the leak hit the scientific community like a silent detonation. If accurate, it means the object is not just geometrically anomalous, it's physically anomalous. It behaves as though it were built to minimize its thermal signature, to flatten its detectability, to remain quiet as it slides along the ecliptic. That alone would be enough to fracture consensus. But just as the debate over the leak reached its peak, another anomaly surfaced. A single streak. A brief, contested, almost dismissed flash captured by a navcam that some say was never supposed to be recording. The first frame appeared on a private research server just after 200 hours UTC on October 5th. It was a single, raw navcam image taken by a surface rover on Mars, never intended for public release at that stage. At first glance, it looked unremarkable. A blurred horizon line, scattered dust particles, and a streak cutting diagonally across the frame. But within hours, that streak had become the centre of a fight that split the astronomical community down the middle. Officially, no imaging of 3i Atlas was scheduled from that rover during the flyby. Orbital assets were supposed to carry the main load. The navcams mounted on surface platforms are designed for navigation, not deep sky tracking. Their sensitivity is limited, their exposures short, their fields of view narrow. For an object as distant as 3i Atlas to appear in one of those frames, a near-perfect alignment would be required. And yet, the streak was there. Engineers at the site where the data originated insisted it was noise. They claimed it could have been a cosmic ray strike, a hot pixel chain, or an unrelated atmospheric reflection. These are all common in Mars imagery, especially during periods of high solar activity. But astronomers who analysed the raw file weren't so quick to dismiss it. Here's what they noticed. The streak's angle, duration, and intensity lined up almost exactly with where 3i Atlas should have been visible from that location on Mars at that exact time. A few minutes of careful calculation were enough to show that if the camera had happened to be facing just a few degrees off-centre, the trajectory of the object would have intersected its field of view at the precise moment the image was taken. The odds of that happening by chance are low, not impossible, but low enough to demand scrutiny. What made the image even more provocative was the streak's consistency. Cosmic ray strikes usually leave irregular pixel-saturated artifacts. This one was straight, smooth, a thin diagonal band fading gradually along its length, showing no pixel bleed. That's not what random noise looks like. That's what a high-velocity object crossing the field of view during a short exposure looks like. The data file itself carried another clue. The streak's intensity profile along its length showed subtle modulation, not a uniform line, but slight rhythmic variation in brightness. Some analysts suggested this could correspond to a rotating body with reflective surfaces catching sunlight in oscillating bursts. Others argued it was simply a digital compression artifact. As word of the image spread through academic channels, a strange silence descended from official sources. No statement, no confirmation, no denial. The navcam frame remained unreferenced in any mission logs. Yet off the record, multiple engineers confirmed that the image was real and that its origin could be traced to a scheduled calibration sequence, one that happened to be running during the object's closest approach. That coincidence only made the speculation louder. By October 6th, high-resolution enlargements of the streak circulated through private Slack channels, signal groups, and closed academic boards. Experienced image analysts began dissecting the angle. One group overlaid it with predicted sky coordinates of 3i Atlas at the exact moment of capture. The result, less than a 1-degree deviation. For something dismissed as noise, that was a little too close for comfort. The reaction was predictable. Skeptics dismissed the analysis as pattern hunting, the human tendency to see meaning where none exists. They pointed out that one matching angle does not prove anything, especially with a single uncorroborated frame. But supporters countered with a sharper point. This was the only unsanctioned visual evidence to emerge during the entire Mars window. And then the most unsettling part emerged. A second image, captured just minutes later by the same navcam system, was quietly flagged in internal telemetry. It never made it to the same servers, but a checksum entry in the rover's downlink log confirmed its existence. No frame was released, no explanation given. The log was there, the image was not. For many, this was enough to turn the streak from a curiosity into a symbol, the single, fragile sliver of data that slipped through during a tightly controlled blackout. Whether real or coincidence, its timing could not have been worse for those trying to keep the narrative simple. The Mars flyby had already been marred by missing high-resolution orbital imagery. The thermal leak was raising uncomfortable questions. Now, a navcam had apparently seen something it wasn't supposed to. The incident sparked a subtle but measurable shift in the conversation. Up to this point, skepticism had been easy to maintain. The absence of data could be blamed on technical limits, but this was different. This was data appearing despite the blackout. Something unsanctioned, something small but sharp enough to pierce the silence. It also raised a deeper operational question. If a random rover on Mars could accidentally catch 3i Atlas in frame, what had the orbital assets seen? What other frames existed, archived, classified, withheld, that might show more than a streak? The silence around the navcam streak became as suspicious as the streak itself. Official channels never acknowledged it. But the absence of denial was to many an answer in itself. And as analysts pored over every pixel of that faint diagonal line, another connection emerged. The streak's direction, when plotted against the object's broader heliocentric path, pointed toward a region of sky whose coordinates had already been burned into the history of the search for extraterrestrial intelligence. The streak event might have been small, faint, and easy to dismiss, but it gave analysts one piece of hard geometry, a direction. When they plotted the trajectory of 3 Atlas across the Martian sky, at the exact timestamp of the navcam frame, they noticed it pointed almost perfectly toward a region of deep space, long associated with one of the most famous unexplained radio detections in history. The coordinates of the WOW signal, recorded on August 15, 1977, the WOW signal came from the constellation Sagittarius, from a point close to the Chi Sagittarii star group. It lasted for 72 seconds. It was never repeated. Despite decades of targeted follow-ups, the exact source was never confirmed. For most of the scientific community, it remains a statistical ghost, neither proven extraterrestrial contact nor definitively debunked. But to those who've spent their lives combing through anomalies, those coordinates have weight. And now, for the first time in nearly half a century, an interstellar object was travelling on a vector that, when extended backward along its path, passed near that same patch of sky. This doesn't mean 3i Atlas came from the exact point of the WOW signal. Space is not a straight line. Orbits bend, gravity deflects. But the alignment is close enough to raise eyebrows, less than 3.4 degrees of deviation between its inbound trajectory and the region associated with the signal. Statistically, that's not proof, but it's not meaningless either. When combined with its abnormally low inclination, stable velocity and flat thermal signature, it starts to feel like a thread pulled from a much older story. Analysts split quickly into camps. The cautious reminded everyone that the WOW signal was never traced to a physical object. Its origin could have been natural, a passing comet, Earth-based interference, or a transient astronomical event. The alignment could be nothing more than coincidence, but others pushed back, noting that coincidence after coincidence is not a neutral pattern. It's a weight that accumulates, and this object had already piled up far too many. Trajectory reconstruction teams from multiple observatories began reanalyzing the object's inbound path. If 3I Atlas originated near the Chi Sagittarii region, it would have travelled through interstellar space for at least 50,000 to 80,000 years, depending on its velocity profile. Its incoming hyperbolic excess velocity matches what you'd expect from a body arriving from that general galactic direction. More intriguingly, its path is too clean for an object deflected multiple times by stellar interactions. It suggests a long, uninterrupted journey. That too is rare, and yet the data is incomplete. Much of the precision tracking from its inbound phase remains classified or unreleased. Observatories that normally publish trajectory solutions for objects of this type have issued only partial orbital elements, citing pending analysis. Independent teams have attempted to reverse engineer the path, but without full astrometric data, their models carry significant uncertainty. Even so, the symbolic weight of the WOW! Signal connection has already escaped the academic domain. Within days of the alignment being discussed in private research forums, it leaked onto public feeds. It didn't take long for conspiracy channels, fringe theorists, and alternative science groups to seize it. Narratives started spinning fast. Claims that 3I Atlas was returning to the signal's origin, that the signal itself had been a ping, that what we're seeing now is the response. Of course, most of those claims lack evidence. But here's the uncomfortable truth. The silence from official agencies only amplifies them. Every blackout, every withheld image, every non-statement becomes fuel for speculation. And in the absence of hard data, the story of 3I Atlas is being written by those outside the official chain. Inside scientific circles, the conversation is quieter but no less tense. If the object's inbound trajectory is linked even loosely to the WOW! Signal's coordinates, then two possibilities emerge. The first, coincidence. A natural interstellar fragment happens to arrive from a historically charged patch of sky. Statistically improbable, but possible. The second, intentionality. A trajectory chosen to pass through, or originate from, a point that once emitted the most famous unexplained radio signal in human history. Neither conclusion can be proven yet, but the alignment is too sharp to ignore and time is running out. With each passing day, 3I Atlas edges closer to the Sun, and the ability to observe it cleanly narrows. There's another layer here, one that doesn't involve the object at all. While 3I Atlas slides into the blind spot, telescopes across the system are busy detecting other signals, other phenomena. A new kind of observation is emerging, one that reframes how anomalies like this are understood. While 3I Atlas slides toward the Sun's glare and silence deepens around its behaviour, another kind of signal has arrived, not from a covert leak or a faint streak on a rover's navcam, but from the most advanced telescope humanity has ever placed beyond Earth's atmosphere. A new data release from the James Webb Space Telescope has revealed something extraordinary. The first unambiguous thermal and chemical mapping of a moon-forming disk around a young gas giant 625 light-years away. The contrast between these two events couldn't be sharper. On one side, 3I Atlas, an interstellar object of unknown origin surrounded by blackout windows, missing imagery, and whispered leaks. On the other, a structured, pristine dataset showing a planetary nursery with breathtaking clarity. This isn't just about different discoveries. It's about what the scientific community chooses, or is allowed, to make public. The disk, observed with Webb's mid-infrared instruments, shows clean thermal gradients, distinct chemical layers, and shock-heated material consistent with active moon formation. For the first time, scientists can see the building blocks of future moons swirling in real time around a distant world. Molecular fingerprints of water vapor, silicates, and complex organics are visible, mapped with a precision so fine that the orbital structure of the disk can be reconstructed from spectral shifts alone. It's the kind of data set that makes a mystery like 3i Atlas feel even heavier. Because here is a distant system, hundreds of light years away, where transparency is total. Every photon is shared, every graph is published, every spectrum laid bare. And here, within our own solar system, an object drifts silently, and the data vanishes into classified voids. This is not lost on the scientific community. Over the past weeks, quiet frustration has been growing among astronomers. They can map exoplanetary disks in exquisite detail, reconstruct distant galaxies from gravitational lensing, and trace faint radiation from the edge of the observable universe. But when it comes to a bright, trackable object less than a single astronomical unit away, the response is silence. The timing only sharpens the contrast. The Webb release arrived just days after the Mars flyby blackout, as if to underline how capable modern astronomy really is. If Webb can detect silicate vapor around a moon-forming world 625 light-years away, what could Mars orbiters have seen at a distance of a few million kilometers? What could ground-based observatories have resolved, had they been given unfiltered access? It also raises another unsettling question. How much of the blackout is about not being able to see, and how much is about not being allowed to? Behind the scenes, several research groups have already begun drawing parallels between these events. One group based in Europe described it bluntly in an internal memo. We can observe chemical processes in alien star systems in detail, but we cannot obtain a single confirmed high-resolution image of a body inside our own neighbourhood. This asymmetry is not technological, it is administrative. That line struck a nerve because it's true. The contrast isn't about capability, it's about access. And access is being shaped not by physics, but by policy. Meanwhile, the Webb data itself carries another layer of implication. The moon-forming disk isn't just a marvel of planetary science, it's also a reminder that the universe is full of environments capable of creating worlds, satellites, and potentially stable niches for life. What we're seeing 625 light-years away is a system in the act of construction, a cosmic workshop, and while our gaze is fixed outward, something closer is slipping beneath the line of observation. The scientific conversation around 3i Atlas now lives in the shadow of this contrast. If an anomaly exists, but the tools to observe it are withheld, what fills that vacuum isn't clarity, it's speculation, and speculation has already begun to accelerate faster than data. The timing of Webb's discovery isn't just coincidental, it anchors this moment in history, a moment where our instruments have never been sharper, our ability to peer into cosmic processes never more powerful, and yet our understanding of what's happening right next to us grows more opaque. This gap between what we can see and what we're allowed to know is widening, and that gap is becoming part of the story. Because as Webb looks out, other technologies are turning inward. Quantum systems, once theoretical, are now maturing. Computation and modelling capabilities are transforming how science interprets ambiguous data, even in the face of silence. As the public conversation around 3i Atlas becomes clouded by blackouts, leaks and speculation, another quieter revolution is underway. While the object drifts toward the Sun, laboratories on Earth are stepping into a new technological phase, one that may determine how we interpret events like this in the years to come. The tools of science are no longer just telescopes and detectors. They are quantum systems, self-improving AI models, and energy reactors capable of sustaining stable fusion reactions longer than at any point in history. In early October, just days before the Mars silence, a milestone was announced: the first sustained, error-corrected run on a fully functional quantum processor. This wasn't a lab demo, it was a continuous operational cycle in which noise was corrected in real time, something researchers had projected would still be years away. The implications are staggering. Where classical supercomputers might take months to brute force the modelling of complex gravitational or thermal interactions, these systems can compress those calculations into hours or even minutes. This changes the nature of an investigation like the one surrounding 3i Atlas. Normally, analysts rely on weeks of number crunching to reconstruct inbound trajectories with precision. to model gravitational perturbations, predict thermal behavior, and estimate structural composition from limited sensor data. But with quantum-assisted computation, even sparse fragmented information can be inverted, cleaned, and recombined to reveal hidden structure. In other words, the silence surrounding the object might no longer guarantee ignorance. The timing is uncanny. In the same month that 3I Atlas moves through its final visible corridor, humanity's capacity to process deep space data makes a leap forward. What was once too complex to model is becoming solvable, and that has not gone unnoticed by the agencies holding the unreleased data. Behind closed doors, multiple research groups are quietly building shadow reconstructions of the object's behavior, using fragments of public light curves, leaked thermal readings, and inferred trajectory data. They are running predictive simulations on quantum clusters. These aren't perfect models, but they're revealing something disturbing. The object's movement is too clean to match the expected drift of an icy or rocky fragment. It behaves as though it is actively stabilizing itself against solar perturbation. One European team described the result in stark terms. The residual acceleration noise is lower than any comet we have ever modeled. This is not the statistical tale of natural behavior, it's something else. This convergence of technology and anomaly extends beyond computation. Advances in fusion energy are accelerating as well. A record-breaking steady-state plasma confinement was achieved just last month, pushing humanity closer to energy systems capable of supporting sustained deep space infrastructure. At the same time, AI-driven systems are now processing vast amounts of observational data from multiple observatories, spotting patterns that human analysts might have missed or dismissed as noise. This matters because the conversation around 3I Atlas is not happening in isolation. It's unfolding against a backdrop of accelerated capability. For the first time, the gap between discovery and interpretation is shrinking, but access to the raw signal remains locked. In practical terms, this means those who control the data control the narrative. Those who control the computation control the counter-narrative. And it's here that the story becomes larger than the object itself. Because this isn't just about an interstellar anomaly. It's about a scientific community standing at the edge of a new era, while an event unfolds in real time. If the silence is strategic, it may not last forever, not when computation can peel through fragments and recover what's hidden. The quantum leap also changes the scale of what can be inferred. Gravitational microsignatures, subtle velocity perturbations, hidden outgassing patterns. All of these can be reconstructed from surprisingly little data. A single streak image, a flat thermal curve, a sliver of trajectory can now seed entire simulations that may expose behavior no one intended to reveal. And in the shadow of this quiet computational arms race, another signal is emerging. Not from the object, but from beneath Mars itself. A geological whisper that has nothing to do with alien signals, but everything to do with what we are prepared to find. While the global conversation is locked on 3I Atlas, a different kind of signal quietly emerges from the surface of Mars itself. Not a streak across a camera, not a missing image, but something buried in stone. A new analytical report from the Jezero crater sampling campaign has flagged an anomaly, an organic molecular structure embedded deep within a core sample, dated far older than most previously studied sediment layers. It's not proof of life. But it isn't something that can be easily ignored either. Jezero has long been at the centre of the search for biosignatures. The crater, once home to an ancient lake system, contains sediments that formed in relatively stable, water-rich conditions. It's one of the most promising places on Mars to find traces of past life. For years, scientists have drilled into its layers, pulling up cores that tell a slow, methodical story of geological time. Most findings have been ambiguous, complex but biotic chemistry, mineral formations shaped by water but not biology. But this new signal is different. What caught analysts' attention was a specific pattern in the molecular chain. It's a repeating sequence of carbon-based structures, exhibiting chirality bias, the kind of mirror-handedness typically associated with biological processes. In Earth's biosphere, this bias is universal. In purely abiotic chemistry, it is rare and unstable. To see it persist in a preserved Martian sample challenges long-held assumptions about what was, or might still be, active beneath the surface. The discovery itself came quietly. No televised announcement, no sweeping claims of life on Mars. just a short technical bulletin circulated through research networks, noting structural asymmetry of potential biological origin, requiring further verification. But among planetary scientists, those words are seismic. The timing couldn't be worse, or perhaps more telling. This finding drops at the exact moment trust in official data streams is eroding. Blackouts around 3I Atlas have created a vacuum, and now a possible biosignature arrives from Mars. What should have been a celebrated moment in science is instead absorbed into a larger storm of speculation. Several researchers are already asking the question publicly: if such a discovery is emerging at the same time as a classified blackout over an interstellar object passing Mars, what else might be withheld? That question isn't entirely fair. Planetary core sampling and orbital tracking are separate domains, but perception is powerful, and perception is shifting. Technically, the finding is complex but not sensational. The molecular chain shows lengthwise symmetry, a stable enantiomeric excess, and a degradation profile inconsistent with simple chemical weathering. The core's dating places its formation in an era when Mars likely had stable surface water, an environment that could have supported microbial ecosystems. Whether this is a fossilized remnant of such a system or an abiotic mimic is still unknown, but the implications are profound. If confirmed, it would mean Mars once hosted, or still hosts, some form of organic complexity that mirrors early Earth in surprising ways, and it's not lost on anyone that this discovery surfaced just after 3I Atlas passed through the Martian corridor. Two events, one world, both enveloped in silence and partial disclosure. For the first time, scientists outside official institutions are beginning to connect dots that may not belong together. They're asking why a potentially life-bearing signature on Mars and an anomalous interstellar object near Mars should unfold in the same week, with such different levels of transparency. One is partially revealed, one concealed. The imbalance is fueling a quiet but real rupture inside the scientific ecosystem. A leaked message from a planetary scientist captures the mood succinctly. We're about to make headlines about carbon on Mars while pretending nothing is happening above it, and beneath this tension, another current runs deeper. The tools being used to analyze these biosignatures, ultra-fast AI-assisted spectroscopic decoding, are the same tools that could, in theory, be turned toward whatever data is being withheld about 3I Atlas. If the object is hiding something, the scientific capacity to unmask it is approaching fast. Meanwhile, as Mars whispers of ancient carbon, Earth's computing power accelerates, and the object slides into the sun's shadow. The race is no longer just between scientists and the object, it's between the data and the silence surrounding it. The speed at which science interprets the universe is no longer determined by how quickly telescopes can collect photons, it's now dictated by how fast artificial intelligence can process, cross-reference, and model incomplete signals. For decades, data was scarce and analysis was slow. Mysteries like the WOW signal or Oumuamua lingered in academic limbo because there weren't enough data points to form meaningful models. But in 2025, something has shifted. The power to extract structure from chaos has outpaced the ability to contain it. The story of 3I Atlas is the first to fully unfold inside this new reality. While official channels remain silent, hundreds of decentralized AI clusters around the world are already analyzing every scrap of public information. A single streak frame from a rover, a few thermal readings from a leak, a partial orbital arc. Individually, these are almost meaningless. But when fed into neural inference systems trained on decades of astrophysical data, they become the seeds of prediction, and the predictions are converging. 3 independent AI-driven modeling groups, one based in Japan, one in Germany, and one operating anonymously through encrypted networks, have all produced remarkably similar results. 3I Atlas's velocity profile, course corrections, and thermal inertia are incompatible with a volatile-rich comet nucleus. The models estimate that for the object to maintain such orbital and thermal stability, it would either need a surface composition orders of magnitude more thermally conductive than anything known, or a controlled mechanism compensating for external forces. But what makes this moment different is not just the conclusion, it's the speed. Classical orbital fitting and material modelling might once have taken months. These AI systems are refining and rerunning models every few hours, absorbing new data streams the moment they emerge. Even minor updates, a single new astrometric reading, a low-resolution radio reflection, can trigger cascades of recalculation, sharpening their predictions like a lens bringing a blurred image into focus. This has changed the balance of power in science. Official agencies no longer fully control the pace of discovery. The blackout strategy that once worked, withholding imagery, delaying public reports, controlling timing, now bleeds information instead of stopping it. Every withheld dataset leaves behind statistical fingerprints. Every absence creates a hole that AI fills with inference. One modelling collective describes it this way: silence is a signal. Gaps have shape. Gaps have weight. They tell their own story. This acceleration is not limited to 3i Atlas. AI is doing similar work across cosmology, exoplanet detection, and Earth observation, identifying anomalies faster than traditional review processes can catch up. But in the case of this object, the stakes are different. Because while the Webb telescope data from a distant moon-forming disk is being shared in near real time, the closest anomaly in the solar system is being wrapped in procedural silence. The result is a widening gap between institutional science and decentralized science, and that gap is filling with conclusions drawn outside the control of any single organization. Some are rigorous, others are reckless, but they're spreading fast. By the end of the first week of October, at least 6 independent networks had published trajectory reconstructions suggesting microaccelerations inconsistent with purely gravitational motion. 2 groups proposed that these accelerations align with minimal periodic course corrections. Another flagged an unexplained stability in the object's rotation vector, and one, quietly, without fanfare, published a predictive model showing an intentional deceleration curve peaking around solar conjunction. Whether these models are accurate remains to be seen, but the point is no longer whether the data is fully open, it's that it doesn't have to be. The silence that once delayed interpretation now invites it. AI doesn't need permission to think. This acceleration is forcing a reckoning. When information can no longer be controlled, when analysis happens faster than narratives can be crafted, the strategy of withholding data becomes fragile. Every missing image is now a prompt. Every unexplained maneuver a live puzzle. In the words of one astrophysicist speaking off the record, they can hide the data. They can't hide the math. And yet, even as AI tightens its grip on the puzzle, the foundation of physics itself is under quiet siege. Because some of the phenomena that 3i Atlas embodies don't fit comfortably within the standard models. As the object nears solar conjunction, theorists are being forced to confront something they rarely do in public. The possibility that the problem isn't just the data, it might be the framework itself. Long before 3i Atlas appeared, the foundations of cosmology were already showing cracks. Quietly, methodically, dissenting models had been gaining ground, challenging the elegant but increasingly strained architecture built around dark matter and dark energy. For decades, these concepts were treated less as provisional ideas and more as pillars, invisible scaffolding holding up everything from galaxy formation models to gravitational lensing equations. But now, under the pressure of precise observation and relentless data modelling, those pillars are beginning to tremble, and in that turbulence the arrival of 3i Atlas isn't just a mystery, it's a stress test. What makes this moment unique isn't only the object's behaviour, but how it intersects with an evolving scientific landscape. Just weeks before its Mars flyby, a consortium of cosmologists released a preprint proposing a modified framework for gravity at galactic scales, a framework that, if correct, could account for phenomena currently attributed to dark matter without invoking invisible mass. Another paper, published almost simultaneously, challenged the assumption that cosmic acceleration requires a constant dark energy term. Instead, it proposed a dynamic interaction, something that could produce local anomalies in gravitational fields, particularly for objects entering the inner solar system at low inclination. In isolation, these are theoretical debates, but when viewed against 3i Atlas's behaviour, its smooth trajectory, thermal silence and improbable geometry, the lines begin to blur. For decades, the default response to unexplained acceleration in space has been to push it into the domain of error margins. Tiny non-gravitational forces, outgassing, reflectivity mismatches, but this object isn't fitting into those convenient boxes. Its lack of measurable thermal plume makes non-gravitational outgassing unlikely. Its course is too stable for a chaotic comet, and yet it isn't moving like a simple rock either. That's why, in closed-door discussions, a quiet possibility is being floated. What if the anomaly isn't the object, but the physics we're using to describe it? This isn't the kind of statement anyone in an official position wants to make publicly. Admitting the framework may be wrong is politically and institutionally dangerous, but the private conversations are happening nonetheless. High-level simulation groups are asking whether local variations in gravitational interaction, perhaps tied to larger cosmological structures, could explain a corridor of anomalous motion without invoking propulsion or technology. Others go further, proposing that if the object entered the solar system through one of these gravitational low-turbulence pathways, its stability might not be surprising at all. The implications are staggering. If true, it wouldn't just reframe 3I Atlas. It would force a re-evaluation of how interstellar objects move, and by extension, what we think space itself is doing. This possibility doesn't rule out intelligence behind the object, but it complicates the narrative. It means 3I Atlas could be both an anomaly and a mirror, reflecting back the limits of our cosmological language. Of course, the orthodoxy pushes back. Major observatories and agencies still lean on the standard lambda CDM model, a universe ruled by dark matter scaffolding and dark energy acceleration. The problem is that the latest high-resolution sky surveys have produced results that are inconsistent. Measurements of cosmic structure growth don't match predictions. Lensing data from distant galaxy clusters shows statistical drift. And some gravitational anomalies closer to home, subtle, persistent, long dismissed as noise, are being re-examined through a different lens. Into this fracture steps 3I Atlas. It isn't just a foreign body, it's an event, one that sits perfectly at the intersection of old physics, new instruments, and rising doubt. Every kilometre it travels along its razor-straight ecliptic path is a reminder that the universe doesn't always fit our diagrams. One theoretical group has quietly circulated a working paper with a provocative line at its core. If 3I Atlas obeys a law we haven't named yet, the silence surrounding it is not just strategic, it's structural. That statement, stripped of drama, is a bombshell. It suggests that some of the reluctance to disclose observational data might not stem solely from the nature of the object itself, but from what acknowledging its behaviour would imply about the models underpinning decades of cosmology. And in the background, there's another force shaping the narrative: private industry. The night sky is no longer just the domain of national observatories and academic institutions. Commercial networks, operating hundreds of telescopes and surveillance satellites, are watching too, and they aren't bound by the same protocols of silence. For most of the space age, the night sky belonged to governments. Major discoveries, tracking systems, deep space surveillance, all of it ran through national agencies, often behind classified doors. But in 2025, that monopoly is broken. Thousands of satellites are no longer owned by governments but by corporations, universities, private networks, and semi-public research collectives. In this fractured ecosystem, silence is no longer absolute. If an anomaly crosses the sky, someone else is watching. 3I Atlas is no exception. Shortly after the Mars blackout, faint traces of unregistered telemetry began appearing in open radio archives, not from the traditional deep space networks, but from private arrays run by independent organisations in Europe, Australia, and South America. Unlike state networks, these arrays have no clearance protocols, no political layers, no need to hold data pending review. They simply record what they see. Within 3 days, at least 4 private observatories confirmed off the record that their optical and radar telescopes had acquired weak but consistent returns from the object during its post-Mars trajectory. The signals weren't rich in detail, but they were real. Reflections, polarization shifts, and Doppler returns that lined up almost perfectly with the projected orbital path. This means that, even as state agencies remained silent, parallel streams of raw observation were quietly accumulating beyond their control. Here's where things get complicated. Unlike state observatories, these private operators don't have a single coordinated protocol. They operate in fragmented pockets. Some share data openly, others guard it for profit, and still others are bound by NDAS with defense contractors. This creates an unstable, chaotic ecosystem where the truth is partially visible, partially sold, and partially buried. And in that chaos, leaks are inevitable. One particular leak hit the scientific underground like a detonation. A small Argentinian radio array, part of a privately funded sky surveillance program, released a narrow-band Doppler trace captured on October 11th. It was faint but unusually stable. Instead of the smeared or noisy frequency shift expected from a tumbling body, it showed a near-perfectly constant return curve over several minutes. That kind of clean profile usually implies a stable rotation, or, more provocatively, active orientation control. At first, mainstream analysts dismissed the trace as poor filtering. But when a Scandinavian optical telescope independently confirmed a synchronous polarization change, dismissal became harder. Two separate networks, operating without coordination, recorded different signatures that pointed toward the same reality. The object isn't behaving like a free-flying chunk of rock. This is where private networks become both powerful and dangerous, because unlike national agencies, they don't need permission to speak. Their motives are mixed. Some are driven by science, others by attention, a few by profit. But once data leaks into this sphere, it can't be pulled back. It becomes viral. It becomes ungovernable. And that's exactly what's happening. By mid-October, fragments of raw data, tracking logs, signal analyses, incomplete radar traces are proliferating across encrypted forums and academic backchannels. None of them alone are conclusive, but together they form a patchwork that increasingly mirrors the private AI models built in parallel, the same clean trajectory, the same suppressed thermal noise, the same micro-stability signatures that shouldn't exist for a natural comet. This isn't just eroding the information monopoly, it's dismantling it in real time. The silence from national agencies is becoming harder to sustain when private networks keep filling the gaps. What was once a single, controllable narrative is now an expanding mesh of evidence, decentralized, inconsistent, but relentless. One scientist compared it to watching a dam crack from the inside. The pressure isn't loud at first, but once it breaks, no one controls the flow. The arrival of commercial space into this mystery also introduces another variable: incentives. Several major satellite operators now possess high-aperture sensors capable of observing 3i Atlas, even as it nears solar conjunction. Their business models thrive on visibility, and that means sooner or later, something they see may not be easy to keep quiet. This is where everything begins to pivot. Because if even a single credible image or trace emerges from these private systems that contradicts official silence, the entire narrative collapses in an instant. Not through a press conference, not through a scientific paper, through a leak. And this inevitability, the certainty that someone, somewhere will see what's not meant to be seen, is forcing state actors to make choices. Some are doubling down on silence, others are preparing for controlled disclosure, and a few may already be feeding limited fragments into private networks to shape what emerges. What began as a single interstellar anomaly is now a race between information control and information entropy, and the entropy is winning. But even as the private sky fills the gaps, the heart of the problem remains the same: the black box of unreleased data. The silence surrounding 3i Atlas isn't just about what has been seen, it's about what's deliberately held back. At the core of this entire unfolding narrative, beneath the streaks, the leaks, the private detections, and the whispers of theoretical upheaval, there is a hole. A deliberate, carefully maintained hole where the most critical data should be. Every credible anomaly surrounding 3i Atlas eventually collapses into this same void. No high-resolution Mars flyby imagery, no confirmed thermal maps, no direct radar returns from government arrays, no clear telemetry from its closest approach corridor. This isn't the absence of data, it's the containment of it. For weeks now, this silent reservoir has shaped everything else. It dictates what private networks can speculate on, what AI models can infer, what scientists can debate. The entire story of 3i Atlas has been unfolding around the gravitational pull of what isn't shared. In ordinary circumstances, this kind of silence might delay public knowledge for months, but these are not ordinary circumstances. The more sophisticated our analytical tools become, the less effective withholding becomes. High-inference systems reconstruct movement from minimal input. Radio networks pick up weak signatures on the periphery. Even amateur telescopes, cross-referenced across time zones, can sketch trajectory deviations with surprising accuracy. And yet none of it replaces the missing core, the direct high-fidelity data that only a handful of orbital assets possess. It's no longer a question of whether those assets observed the object. Everyone knows they did. The object passed well within their sensor range, close enough for high-resolution thermal scans, radar reflections, and detailed spectral analysis. What remains hidden is the content of those observations. That silence is no longer neutral. It is now an active force shaping global perception. In that vacuum, speculation metastasizes. Competing interpretations stack like unstable scaffolding. Some narratives stay within the boundaries of physics: stable trajectories, unorthodox surface compositions, gravitational corridors. Others cross into far more volatile territory, talk of hidden probes, deliberate approach vectors, and strategic invisibility. What makes this gap especially volatile is that both camps feed from the same silence. Scientists need real data to ground the discussion. Speculators need silence to build mythologies, and so far the latter is gaining ground faster. Inside several agencies, internal documents have begun to surface, not full data drops, but meta-level language hinting at how the situation is being framed behind closed doors. One describes the current environment as information fragmentation with escalating external inference risk. Another, more bluntly, every hour we don't release anything, someone else invents their own version. The gap is reaching a critical mass. If nothing emerges soon, the story will be owned entirely by those outside the system that actually holds the truth. And once that happens, it won't matter what the data shows. Perception will have already won. There are precedents for this. During past astronomical events, large-scale impacts, transient radio anomalies, unconfirmed signals, delays in official communication allowed misinformation to take root so deeply that no subsequent correction could fully undo it. 3i Atlas is on track to become the largest of these information fractures yet, because this time the object isn't at the edge of the solar system. It's right here, cutting through the ecliptic like a blade through silk, and the timing is merciless. In less than 2 weeks, the object will disappear behind the sun, entering a window where direct optical tracking from Earth-based systems becomes impossible. If official data remains buried during that period, whatever emerges afterward will not be treated as a clean, trusted report. It will be seen as controlled narrative for the people inside this machine, scientists who know there's more on the other side of the wall. This is creating deep fractures. Some advocate for full disclosure, arguing that public trust is already eroding. Others cling to silence, convinced that premature release of incomplete or politically sensitive data could destabilize institutions. And somewhere between those positions lies the object itself, moving steadily toward the solar limb. This is what happens when technology outpaces governance. The truth can't be contained indefinitely, but its release can be delayed long enough to poison the conversation that surrounds it. And that conversation is approaching a breaking point. Because after the blackout and the silence, there comes a moment when theories collide, a moment when the story can't be stretched further without something snapping. For all the silence, leaks, and speculation orbiting 3i Atlas, a fixed point is now looming on the horizon, a global coordination window. A handful of scheduled deep space radio checks, narrowband, high sensitivity, cross-reference between multiple arrays, will soon begin. They won't answer everything, but they could end entire branches of speculation overnight, or confirm the one possibility everyone has been circling around without saying out loud. The coordination began quietly. A small coalition of observatories and universities, frustrated by the lack of official disclosures, initiated what they call a distributed verification campaign. Rather than waiting for a centralized green light, they aligned their observation windows in the days before the object's solar conjunction. Their plan is simple: build an independent, redundant record. Multiple ground stations, operating on synchronized frequencies, pointed at the same coordinates at the same time. The backbone of this campaign involves radio interferometry, linking widely separated antennas to increase effective resolution. The participating networks include mid-range radio dishes in Australia, Spain, Canada, Argentina, and South Africa, as well as one small array in Morocco recently repurposed from meteor tracking. These aren't the massive deep space facilities used by national agencies, but when synchronized, they can pick up faint Doppler shifts and narrow-band emissions that would be invisible to individual stations. What they're looking for isn't a Hollywood beacon. They're not expecting a modulated transmission or a deliberate broadcast. They're looking for subtler fingerprints, anomalous Doppler drift, coherent polarization rotation, reflective signatures that betray structure, not chaos. A natural body emits and reflects in messy, scattered ways. A structured body, even an inert one, reflects cleanly. It's the difference between listening to wind across pebbles and wind across polished steel. These tests will also probe something more fundamental, whether the object's course corrections are real or an artifact of patchy tracking. If it's truly maintaining its path with near-zero drift, the consistency of the Doppler curve will expose it. If there's hidden propulsion, whether active thrust or an exotic stabilizing mechanism, it won't be in the images. It will be in the radio spectrum buried in the subhertz shifts of reflected signals. And here's the crucial part. These observations will happen outside of official channels. No clearance, no redacted briefings. The data will be collected simultaneously by multiple groups across the globe, each archiving their raw signal independently. It's a direct counter to the information gap. Even if one network is pressured to stay silent, the others can release their version of the signal. Officials are aware of this. It's why internal memos have grown sharper in tone in recent days. One describes these parallel observations as an uncontrolled narrative vector. Another warns that any external confirmation of non-natural signal characteristics will severely limit narrative maneuverability. It's language that reveals just how brittle the current information structure has become. For the scientific community, this is more than a technical exercise. It's a moment of epistemic fracture. If the object behaves exactly like a comet or a dark rock, much of the narrative collapses. The blackouts, the leaks, the speculation, all of it will fade, replaced by mundane explanations. But if the signal isn't clean, if it shows coherence where there should be noise, if the trajectory remains unnaturally perfect, then the blackout becomes something else entirely. It becomes a containment strategy in the face of an event they can't yet define. Every major scientific inflection point has its test moment, a quiet technical hinge that history later remembers as the place where everything changed. The Michelson-Morley experiment, the first cosmic microwave background detection, the first gravitational wave chirp, and now, perhaps, the first global unsanctioned radio campaign aimed at a single interstellar visitor. The researchers involved know they might find nothing, but that nothing would itself be an answer. What they're building is a fork in the road, a moment where two realities can no longer coexist. One where the object is extraordinary only in rumour, and one where it is extraordinary in fact. And as the clock ticks toward October 29th, that window narrows. Every hour the object moves closer to the solar limb, the harder it becomes to track. Every day the signal weakens. This is the final stretch before the silence becomes total. But silence can only hold so long, because once the tests are complete, once the signal is either heard or not, the narratives built in the dark will face the light of measurable reality. And when they do, the theories will collide. As the radio coordination window draws near, something begins to shift, not in space, but on Earth. The narrative threads that have been pulling in opposite directions since the first blackout are tightening like cables under strain. For months, the discussion around 3i Atlas has been an uneasy dance between two worlds, the careful caution of astrophysics and the growing momentum of technological speculation. In the coming days, these worlds will collide. The naturalists, astrophysicists, orbital dynamicists, thermal modelers have held their line with discipline. They argue that however strange 3i Atlas appears, nature has room for outliers. Interstellar space can produce improbable geometries. Ejection events from young star systems can fling objects into low-inclination, high-stability corridors. Exotic surface compositions could account for unusual reflectivity. Even its clean thermal profile, they argue, could stem from an unknown mineral structure, something not yet catalogued but still natural. Their position isn't naive, it's rooted in history. Anomalies almost always collapse into ordinary explanations when enough data is gathered. But their confidence is fraying. The blackouts were their first fracture point. The lack of a single clear Mars flyby image left them defending something they couldn't see. The thermal leak, steady, unnatural, structured, forced many to quietly revise their models. The streak event on the rover camera injected geometry they couldn't fully dismiss, and now the leaked Doppler traces from private arrays are carving hairline cracks in what was once a solid wall. On the other side of the divide stands a coalition of technologists, signal analysts, and a growing number of physicists who suspect something more deliberate. They aren't claiming extraterrestrial intent outright. Not yet. But they see a chain of behaviour that looks engineered. The low inclination trajectory that maximises gravitational stability, the precisely timed solar disappearance, the steady thermal output, and the eerie alignment with the WS OW signal corridor. To them, this doesn't look like nature's randomness. It looks like structure. And structure changes everything. Their argument isn't built on proof. It's built on the absence of noise. Nature is messy. It jitters. It fluctuates. It drifts. But 3i Atlas doesn't. It moves like something maintaining a set point. It emits like something dampening fluctuations. It reflects like a stable surface, not a tumbling aggregate. Theories have already emerged in these circles. An artificial shell stabilizing an inert core, a probe-like structure coasting on gravitational highways, even long-decayed remnants of something built far away and long ago. It's not proof, but it's no longer fringe either. This is the critical moment in every scientific anomaly, when both camps have just enough data to fortify their own beliefs, but not enough to disprove the other. In this liminal zone, the debate becomes sharper, harder, almost personal. Teams begin drafting preprints before the data even arrives. Private arrays align their clocks. Agency scientists whisper in hallways but refuse to go on record. And in the background, political pressure mounts. Governments fear one thing above all: losing narrative control. If the object turns out to be ordinary, releasing data too late risks fueling a myth. If it isn't ordinary, delaying too long may make the myth unstoppable. Either way, their grip is slipping. Private observatories are ready to publish. networks are running 24/7 simulations. Radio dishes are locking onto their final observation arcs. This collision won't happen through a single announcement. It will happen through an avalanche of competing truths. One group will post its clean Doppler trace, another will release inferred trajectory models. Someone else will publish high-frequency signal noise analysis claiming faint modulation signatures, and state agencies, forced into daylight, will finally release fragments of what they've been holding. But by then they won't be shaping the story, they'll be reacting to it. What happens next depends on what those signals say. If the returns show a chaotic, noise-dominated signature consistent with a natural body, the technological theories may fracture, but they won't vanish. The months of silence have seeded too much doubt for any single report to fully restore trust. If the returns show structure, clean polarization curves, coherent micro-adjustments, or unexplained modulation, the naturalist camp will face its most serious challenge in decades. And beneath the debate lies a quieter, more sobering truth. If 3i Atlas is more than rock and ice, the thing itself is still out there, moving in silence, crossing the solar plane like a needle through cloth. No press release can change its trajectory. No debate can slow it down. The collision of theories is happening here, on Earth, but the object remains unmoved. In a sense, this is how paradigm shifts begin, not with clarity, but with fractures so deep that old frameworks can no longer hold their shape. And just beyond this collision, on the other side of the sun, the object will re-emerge. Whether it's confirmed as mundane or revealed as something else entirely, what comes after won't be the same as what came before. The solar limb is near. In less than 48 hours, 3i Atlas will cross behind the sun and vanish from nearly every optical instrument on Earth. The tracking networks, already strained by interference and geometry, will lose their clean line of sight. Observatories will fall quiet, replaced by a thin thread of low-frequency radio monitoring and predictive modelling. For the first time since its arrival, the object will not be visible, only inferred. In astronomy, this kind of disappearance is routine. Comets, asteroids, even interstellar visitors slide behind the sun and emerge days or weeks later, their paths unchanged. But nothing about this event feels routine. For months, 3i Atlas has existed not just as a celestial body, but as a fracture in the way the world understands and communicates about the cosmos. It's more than a trajectory, it's a mirror. It has reflected every pressure point, scientific, political, technological, in a world that can no longer keep secrets the way it once could. As it approaches conjunction, the signal is already fading. The last clean Doppler returns are getting thin, scattered through solar interference, peppered with bursts of static. Tracking teams around the globe are synchronizing their final passes. At least 9 independent arrays, and most of them private or university-operated, will continue recording long after official agencies log out. These recordings won't be clean, but they'll be enough to tell if anything changes behind the sun. A sudden deviation, a frequency break, a silence too sharp to be natural. No one is expecting an announcement. Not now, not in this last stretch. What hangs over this moment is something quieter, heavier. The sense that whatever happens behind the sun will define how this story is remembered. If the object emerges on the other side exactly as predicted, on the same curve, at the same speed, with the same dead-straight trajectory, the scientific narrative will have a way to slowly heal. The Mars blackout will fade into an uncomfortable footnote. The streak event will be archived as coincidence. The thermal leak will become an artifact to be explained away. But if the object doesn't emerge where expected, if it accelerates, slows, shifts its course, or vanishes entirely, then the story will not be owned by scientists anymore. It will be owned by history. There is a reason some agencies are preparing controlled statements ahead of the reappearance window, not because they know what will happen, but because they don't. This uncertainty is corrosive. It eats at institutional confidence, at carefully managed narratives, at the assumption that humanity can map and explain everything it encounters in space. 3i Atlas has exposed the limits of that assumption more brutally than any object before it. The last few hours before solar conjunction are quiet, in the way air is quiet before a storm. The A models continue running, folding radio noise into predictive paths. Some projections are so precise they predict emergence coordinates to within a few hundred kilometers. Others drift wildly, forecasting course breaks, sudden disappearance, or impossible shifts. None of these models can be verified until the object comes out the other side. Scientists have a phrase for moments like this, the observational horizon. It's the point where evidence vanishes into prediction, where the universe demands patience instead of clarity. And that's where 3i Atlas lives now, on the edge of what can be known. The object's next move may be entirely ordinary. It may follow the same elegant, silent trajectory it's held since it entered the solar system. But the world it moves through is no longer the same as when it arrived. Public trust has shifted. Private eyes are watching. AI is listening. And the quiet, controlled monopoly over cosmic truth has cracked. No one can say what will emerge from behind the sun. Maybe a comet, maybe something else, maybe nothing at all. But whatever it is, the silence has already changed everything. This is the moment before the verdict. The sky is holding its breath, and somewhere on the far side of the sun the object keeps moving, indifferent to the arguments it's left in its wake. The last telemetry drop came in just after 2:13 UTC, a faint grainy Doppler trace. Nothing spectacular. No sudden flare, no vanishing pulse. Just a quiet, receding signal that tapered into the background noise of the sun. At that exact moment, 3i Atlas crossed the solar limb and was gone, not in the poetic sense, literally gone from our view. No telescope, no camera, no thermal sensor on Earth can track it now. Only equations remain. For the first time since its detection, the object exists entirely in prediction, in orbital ephemerides, in AI-generated trajectories and interferometric models that are already diverging slightly from each other. Some show a clean re-emergence in early November, perfectly aligned with gravitational expectations. Others whisper of deviations just large enough to matter, a slow drift that could signal hidden maneuvering, or nothing at all. Around the world, this moment doesn't land like a headline, it lands like a weight. Inside observatories, the lights stay on. Arrays keep listening even though there's nothing left to hear. Researchers who've spent months obsessing over every scrap of this object now confront a peculiar kind of emptiness. The silence is no longer a tactical choice, it's literal, radio, quiet, optical darkness. And yet, the world outside those observatories is louder than ever. Speculation surges through encrypted forums, dark web threads, and mainstream feeds alike. Every millisecond of missing signal becomes a canvas on which someone paints their own explanation. For governments, this is a dangerous kind of silence, the kind they can't fully shape anymore. Some agencies have drafted preemptive statements, These are careful, balanced, clinical. Trajectory appears nominal. Preliminary modelling remains consistent with natural behaviour. Additional verification expected upon re-emergence, but no amount of controlled language can erase the month that led here. The blackouts, the streak, the leak, the directional alignment with the WOW ! Signal corridor, the private detections, the radio campaign. This isn't just an astronomical event anymore, it's a trust event. At this point, even if 3i Atlas reappears exactly where the equations predict, the fracture it opened won't close. Too many questions were raised in the silence. Too many private actors stepped into the void left by institutional control. Too many people now understand how much can be inferred without permission. The real story may not be what the object is, it may be what it revealed. How fragile the walls of official narratives have become in a world where AI can model an anomaly faster than anyone can suppress it. How the sky is no longer owned by governments alone. How the truth, once fractured, doesn't wait for anyone's approval to spread. In the coming weeks, the object will either re-emerge on schedule or it won't. Either way, the signal will return, or it won't, but the world is no longer waiting passively. Arrays will be locked on the predicted coordinates before dawn. AI inference systems will be running the moment the first photon breaks through the solar interference. Thousands of telescopes, both private and state-run, will converge like a silent jury. The object will have nowhere to hide, and neither will the truth. Until then, there is only this: a quiet curve of orbit disappearing into the sun's light, an Earth full of unanswered questions, and the low, steady hum of machines listening to the silence.